Our final speaker is Ramaswamy. He is the director of the Geophysical Fluid Dynamics Laboratory at the National Oceanographic and Atmospheric Administration, or NOAA, and is a lecturer with the rank of professor at Princeton University. Dr. Ramaswamy is leading his laboratory towards a new era in supercomputing to enable higher resolution and greater complexity in the lab's climate models. Dr. Ramaswamy also has participated on the Intergovernmental Panel for Climate Change, which again co-received the Nobel Peace Prize in 2007. He's the recipient of many honors and awards, including being a 3-time honoree for the WMO Norbert Gerbier MUMM International Award from the World Meteorological Organization. Dr. Ramaswamy is the author of over 150 publications. He earned his bachelor's degree from Delhi University and a PhD in atmospheric science from the State University of New York at Albany. Please join me in welcoming Dr. Ramaswamy to today's conversation.
Okay, good afternoon, everyone. And first of all, I would like to thank Arthur and his team for putting this event together. It's been such a marvelous, entertaining session we had earlier this afternoon. And I also want to thank Alexis for the kind introduction. So I'm going to pick up in some ways from where Michael had talked about results from modeling. I'm a modeler, which means that we do mathematical modeling of the Earth system using fundamental principles in physics, chemistry, dynamics. And the lab that I work in is the oldest climate modeling lab in the world. It built the first global climate model ever back in the 70s. The lab was founded in 1955. It was in Washington, D.C. till about 1967. And then moved into this partnership with Princeton on the Princeton campus. So I'm going to try to do the linkage between climate change and atmospheric processes. I think the oceans were very well done by Stevens. So this is what we are trying to understand. That's the Earth system consisting of the atmosphere, ocean, land, and ice. Now, each one of these components has its own system of equations, has its own physics and chemistry, and has its own time scale for operation. So atmosphere is faster than oceans, oceans are still faster than ice, and land is somewhere in between. So it makes it a complex affair to actually, first of all, formulate a system of equations to represent all these components, and then over and above that, to study the interactions occurring between them. And that's kind of where the model comes in. So my talk's going to be on 3 items, or at least focus on 3 items. One is a challenge of understanding the Earth's climate system, and this consists of the scientific scale of the components that are forcing change, and I'll go through one particular example. Then the modeling itself of the Earth system in a very general way consists of complexity, consists of resolving things so that you are making scientific results available for practical applications, and there are uncertainties, and I'll go through one type of uncertainty. And then finally, an exciting period is coming up where, with the recognition that climate is not stationary, things are changing, as you heard in the previous talks, and there is weather in the context of climate. So can we try to do the weather in the context of climate change is the final topic I want to broach here. So just to capture what's been the reality in recent decades, we've had major advancements in climate science. A lot of it is due to observations, analysis of observations. Observing systems, for example, being put up by NASA, by NOAA. And then computer modeling. And with the advances in high-performance computing, we can go through all these set of equations that are listed here, and we don't have to worry about them today, but essentially trying to carve out the Earth in terms of grids, as you see here, and then using supercomputing to actually conduct the computations. And then it's a three-legged stool, really, where you have observations, you have modeling, and then you have to do the understanding. So it's no use trying to just observe, no use trying to just model. The understanding is the key part, because the understanding is what has to be there before you get to predictions, before you get to reasonable science-based predictions. So, and historically, the activities have started at the large spatial scales. You consider the planet as a whole to determine whether it's warming or cooling, and then you get to smaller spatial scales. And then also in terms of time scales, the climate system has been studied with a kind of a centennial view in perspective, but increasingly now we are going down to the decadal and even shorter time scales to understand the weather now in the context of climate. So Michael has already mentioned a lot about observations, but I'll just go through a couple of observation results coming out of the last IPCC, which was in 2013. One of the things is, it is not just the surface temperature that's warming, that is giving us the indication of a warming world. It is everything that you can think of is going in that direction. So it is not just air temperature or ocean, it is not just air temperature over land, not just sea surface temperature, but you have things like temperature of the lower atmosphere is increasing. And you have humidity that's increasing, which means basically the water vapor in the atmosphere because of warming. And then you have things, that should be decreasing as a result of warming. Arctic sea ice, is showing a decrease. Snow globally is showing a decrease. And then you have glaciers retreating. So it is multiple lines of evidence that convinces us it's a warming world just from observations. Now, another important thing, and of course, sea level is increasing, as was pointed out by Michael and by Steve. And one thing I want to get out is one of the key fundamental things is ocean heat content. In terms of reservoirs of heat in the Earth's system, the atmosphere cannot hold much heat. It's very thin. Land can hold some, but land is only, 28% of the globe. So most of the heat, if there is heating going on, has to go into the oceans. And indeed, this is sort of from the last IPCC, and you can see that while there is uncertainty, but the upper ocean has captured a lot of the heat over the last, 40 years. And there is some in the deep ocean, some which has gone to deep ocean, but land and atmosphere are very small. So you should be able to corroborate this in the observations. And indeed, observations are showing that the ocean heat content is increasing. That, I think, is the single biggest irrefutable thing about there is warming going on. Now, maybe, okay, so you can argue it's only in the oceans, but of course it is manifest even in surface temperatures over land. Now comes the question of understanding. Why has it changed? And here's where we have to consider lots of factors. So first of all is just the internal variability of the coupled atmosphere-ocean system. The atmosphere and ocean are fluids. They run on different time scales. They interact with each other. And so you should expect some kind of oscillations or variations. And indeed that happens. The ENSO phenomena is a classic indicator of that. So there's internal variability of the coupled system. Then there are natural mechanisms such as changes in the sun's output and changes in the amount of volcanic dust in the atmosphere due to the volcanic eruptions. So that's one set of factors that can influence climate, natural factors. Then again, as was mentioned by Mike, there is CO2 increase, but there are also other greenhouse gases which are long-lived, like methane, N2O, and they have curves which look pretty much like CO2 in terms of a continuous increase. CFC11, as you know, is, I hope I can show, yeah. CFC11 is reached a plateau because of the Montreal Protocol and is starting to decrease, although recently, if you saw the science paper, some CFC11 is not continuing to decrease, it has plateaued out. And then there's ozone hole, which ozone is a greenhouse gas too, so that adds to the global warming problem because of its decrease. But again, that is stabilizing, supposedly, and by mid-50s it is supposed to stabilize, although there are uncertainties there. But these are all the influences due to the gases. Then there's the world of aerosols, particulates. So that's also there in the system. And you'll see a lot of circles here. So some of them are human-influenced emissions, ships, smokestacks, cars, trucks, planes. And there are some which kind of don't directly have an effect due to their emissions, but they can affect other things which affect the Earth's energy balance. So there's the chemicals, dimethyl sulfide, and then isoprene emissions from trees. That's also, but these are big players. And then there is natural stuff, natural aerosols like volcanoes, which I already mentioned, sea spray from waves breaking on the surface of the ocean. And then there are some sources which are natural and human influence, such as aridification or desertification, whereby you release dust into the atmosphere, which interacts with the energy balance. And then forest fires, which can be natural and anthropogenic. So the aerosols actually are a little bit of a different set of beasts compared to the greenhouse gases. They have also been influencing the system. And very briefly, the science of the aerosols is not difficult, but in a general way. You have aerosols just scattering. They basically scatter the sunlight and reduce the amount of sunlight to the system. And you have absorbing aerosols, which absorb the radiation from the sun, and they can warm the system. And then you have a more complex effect involving aerosols and water drops, whereby aerosols can interact with water drops and brighten the clouds, so affect the clouds. And then in terms of just the clouds, which is a major uncertainty, but although we are, I think, narrowing the uncertainty there, there's a lot of things which happens with clouds. They can rain, they can form ice, there can be scavenging by droplet coalescence. So I don't want to go into all this physics, but this is kind of very detailed physics, and it does affect the uncertainties, although observations are helping us to pin this down. So in terms of what has forced the climate system, this is the positive part, which is the greenhouse gases, and don't worry about the numbers, it's just on the positive side. And then this is the aerosol, which is the negative side. So the story actually becomes what has happened over the last century between greenhouse gas and aerosol emissions, because they're going in the opposite direction. And to do this, you need the models. And this is just one more schematic of the model where it's showing that you divide the Earth into grids. You have grids going down to the surface of the ocean and then going into the atmosphere. And into this, you form the equations and perform your numerical integrations. And this is, again, one of the models. This happens to be our lab's model, but all models have a similar box diagram where you have ocean, you have the atmosphere consisting of chemistry and all sorts of physics, and then a land, and these are all coupled together, and this kind of forms your Earth system model. So let's look at some results that came out of the IPCC from a collection of the models. So this is not just one model, but as Mike was showing you, there are so many models in AR5, all of them, if you pool the results together, what do you get? So first of all, the observation of the warming since 1951, so it's the last 50 years, is approximately 0.6 to 0.7 degrees centigrade. That's the observed, and that's kind of what you have to explain. And when you look at the results, so with a model can do several interesting things. One of them is that, of course, it substitutes the role of a lab. A typical lab in physics and chemistry, you can actually go and test a hypothesis by walking to the next room or to an actual lab. But in the planetary case, you don't have a second Earth to do experiments with. That's kind of where the computational efforts come in. That's where the models come in. And so the model, you can do anything. You can ask a question as supposing the Earth had been forced only by greenhouse gases over the last century. So that's what that first green bar is. It shows you what the result would be if it were only greenhouse gases. The error bars, because a lot of models involved, represent that bar that you see there. But clearly you see that the green bar cannot explain all the observations because it actually overestimates the observation. Well, then let me go to the solar and internal variability. Those are very small. And these are estimates now done by lots of studies, so they are actually not very significant for this long-term warming. But when you take anthropogenic, which consists of greenhouse gases plus aerosols, you see that this bar matches the black bar pretty well. And that's kind of the reason for the statement that's extremely like the human influence has been the dominant cause, because the anthropogenic actually explains most of it. But you notice there's a large uncertainty because of the aerosols. That's kind of where that uncertainty actually still persists, although we are kind of narrowing it down, as I said earlier. Now, this is actually a more latest information compilation. It shows you some of the issues that you come up in the science. So first look at this upper right panel here. All this yellow thing is really the internal variability as represented by models. Now, typically, in a standard well-posed experiment, if you were trying to isolate isolate a signal from noise, you would have to know what the noise is. Then only you can sort of say, identify a signal. Unfortunately, we don't have observations over several hundreds of years which can actually portray the Earth's internal variability. But you can do it with models. You can run models without any forcing, and that's kind of what you get as internal variability. And notice that the observed warming exceeds that internal variability somewhere around 1960s, 1970s. So this is where the confidence comes in that you extracted a signal from the noise in the global mean temperature. And these are other curves explaining what the different models do. And the pink is exploring the range from the models. And if you do only natural forcing, the bottom left is showing what the natural forcing does, which is essentially nothing. It's a zero trend almost. So there is uncertainty, but this uncertainty is not something that should be stopping the science. It doesn't stop the science of having explained things as being due to anthropogenic influence. So let me get to now the more sort of philosophically broad topic of modeling the Earth system. So increasingly, we are seeing a lot of complexity. The more observations you take, the more you realize what you have not captured. So Earth system complexity is something that increasingly people are trying to capture in all the modeling centers. The other aspect is resolution. So far, global models have been working at something like 2-degree, 3-degree latitude, longitude resolution, which is too vast. You want information down in your county level. Well, that means you have to increase resolution of the model. It means you need more computing power, but it also means understanding the physics at the local scale correctly in order to be able to model that. So one of the recent successes we've had is going to higher resolution in terms of estimating the rainfall over North America. One of the key features, if you look at the observation, this is the observation, and the brown is roughly less rainfall than some amount, and green is more. So roughly there is this line going down the Midwest of the US where to the kind of west of it is pretty dry, to the right of it is pretty wet. And these were the models, for example, used in early days. You can see it's very fuzzy. You cannot get county level information from this. And this is kind of something that we built up in 2014. And this is kind of the latest model. And this is 25-kilometer resolution. So you can see that even though it's not exactly the same as the observation, it resolves some of these fine-scale features seen in the Midwest US. So you can resolve the precipitation. Another thing is heat waves. So one of the things that accompanies warming is heat waves. So in order to prepare the model to be able to be tested and predict future heat waves, you have to first compare the past. So this is a comparison of model versus observation of heat waves. And I won't bother here about the definition. There's a certain definition of heat waves, which is defined by the World Meteorological Organization. But you can see the model that the model over the last 30 years represents the climatological average of the observations. So it gave us confidence to actually go and try to predict the future. And so this is a model projection of heat waves. So this is a ratio of if you look at the last column here, just the last column, it's the number of heat wave days per year ratio. So that it's a ratio in about 2065 to that in 1990. So it's roughly about a 70-year differential. And the US has been split up into different regions, and you can do this actually for any region of the globe. This is only shown for the US. So in each one of these regions, you see a number greater than 1, which means you have to, whatever heat wave days you're getting today, you have to multiply by that number to get what the number of heat wave days per year going to be in the future. So in the Midwest, right now, I think officially the definition is such that it's about 3 days per year, so it's going to go up to 12 days. According to the sort of a mid-level scenario of the projections. And so everywhere it's actually more than 1. So some regions it's actually very, very large. So this is kind of something that now you can do with these Earth system models. The other thing we want to get at is extremes. So heat waves is one kind of extreme, but you want to get at extremes, but you also want to get it at all time scales, not just 70, 100-year projections. In other words, it's asking the question of, we are very confident that given the emissions, the 2100 is going to look in a certain way. That's kind of all models say that. There's no reason to disbelieve them, provided the emission scenarios are what's given. But what about the trajectory from here to 2100, from 1920 to 2100? Can we predict that on different timescales? So first you have to start at the weather timescale. And of course, what we are looking at is trying to really categorize all these kinds of events, whether it's hurricanes, snow, floods, drought, fires, and aridity. So one of the ways, historically, I think the weather and climate models have been different. But now, actually, we've used this climate model that we built to actually do a forecast of hurricanes. And the first test was last year, where the US suffered at least three severe storms, three severe hurricanes. Hurricane Harvey, Hurricane Irma, and Hurricane Maria. And what you're seeing is track. And the way this graph is that this end would be about 5 days out. And then as you're getting closer and closer to the D-Day, you obviously, all models get it right. So there are three models here, and the difference I think you'd look at is between the blue and the others. Blue is the European Central model, which is, in this industry, the best model to predict hurricanes in the Atlantic. And you can see that by, for example, looking at Hurricane Irma, and obviously the lower the number, the best that model was the best because track error was the lowest. So blue is very good. The green and red, which are actually a little bit differences between two essentially similar models, is larger error. But on the other hurricanes, it actually is comparable to the blue. So this is not to kind of showcase competition between these two models, but actually to show that the climate model can actually produce the hurricanes. This is on the weather time scale last year. Then as we go, obviously, we're getting ambitious. We want to go to even longer time scales. So when you go to seasonal and decadal, you would enter into a very classic, different type of problem. So when you are in the climate time scale, which is normally what IPCC talks about, you are in this regime where it's kind of a boundary value problem where the system is responding mostly to the forcing, greenhouse gas, aerosol, and so on. But as you go to shorter time scales, as you go to seasonal time scales, for example, there is an initial value problem, which is much like the weather problem. The way weather forecasts are done is you take the conditions from today, you put it in a model, that's a starting point, and then you predict the weather for tomorrow. Now, because of the fact that it's only 24 hours, the starting conditions matter a lot, and you actually can do a very good forecast these days in 24 hours. But as the time gets longer and longer, you can't rely on just initial value. You have to get the boundary value. But in between time scales, like seasonal to decadal, which you have got a very interesting complexity of problems called the initial value and boundary value problem. That's a tough one because you have uncertainties in the boundary values, you have uncertainties in initial values, and now you're compounding the two uncertainties. But you have to believe that science is advancing, observations are advancing, that you can actually do this problem. This is the exciting aspect of this of the whole weather climate problem now. So we actually used it in the context of two problems. I'll go through it quickly, and that's like the prediction of El Nino. So this is actually hindcasting. It was not actually the prediction. It was after the event, trying to understand it, trying to see if you can predict it. There were two big El Ninos in the last 20 years. One is the 97-98 ENSO, and then 2015-2016. And the observed precipitation distribution, especially over the western US, is this. And the classical pattern that was known before was the fact that you had increased precipitation in the southwest, in California, and not much elsewhere. But the observation pattern for the 2015-2016 was a complete flip of that. Completely eroded all our notions of ENSO precipitation. And then this is now use of the model, the climate model, where with initial conditions coming from the oceans, which was a standard way people used to do this, you reproduce this 97-98 ENSO conditions of precipitation, but you don't for the 2015-2016. You're using the same model, you're using the same methodology, but you don't reproduce that. But it turns out that when we try to use the land initial conditions, so land also determines kind of the state of the atmosphere tomorrow, you actually reproduce this condition. Now, this is just one test and shouldn't be sort of interpreted as having solved the problem, but it does go to show that you can actually engage the model even on interannual timescales, which is what ENSO is. And then this is of hurricanes globally, and this is the model, this is the observation, and I won't go into a lot of details, excepting, you can just see by the red colors are category 4 and 5. Those are the most destructive hurricanes. And you can see that the model actually does capture the observations not too badly. So all this is by way of giving confidence into this new era that we're entering, where we can tackle this weather and climate modeling in a very seamless manner. And finally, this is an example of, again, a prediction, but now talking of air quality, because the very warm weather gives rise to heat waves, which can give rise to stagnant air, which can give rise to air quality issues. So this is actually comparing model simulation of ozone, which is kind of a major air pollutant, measured at Penn State University, Mike Mann's place. And this is actually a simulation of a prediction on June 1, 2012, when there was a large warming occurring in the Midwest, and there was a high pressure ridge, so there was stagnant air, and sure enough, the ozone amount was very high compared to normal. And this is one of the instances which gives rise to the possibility that you can explore now smog levels occurring during heat waves, and just by through the temperature extremes. So seasonal predictability of temperatures can actually give rise to understanding of air pollution extremes, which goes to the idea of there are multiple stressors in the system. So increasingly, the models are trying to get to where the impacts are. So not just predicting temperatures, not just predicting rainfall, but actually getting to more downstream. And this is my final slide, which kind of condenses where we are. And this follows actually National Research Council 2012 recommendation, which was for the modeling centers to try unified modeling approaches so that you can actually go all the way from weather timescale to climate timescale. And there are a number of phenomena here that I've listed here. You have on a short timescale, tornadoes, snowstorms, hurricanes, typhoons, then going on to heat waves, going on to El Nino, precipitation extremes, changes in the Arctic, and then decadal to multi-decadal, and then finally you go to things like sea level rise and ocean circulation. And you have internal variability, you have external forcings, you're going to have to deal with that. And the important thing is going back to the sort of what I mentioned earlier, that climate is non-stationary. So you're going to have variations, you're going to have extremes superposed on the trends, long-term trends that are imposed by greenhouse gas emissions. So that's all I had, and thank you very much for your attention. Oh, yeah.
Okay, make sure you're getting your questions to our students. And as we're doing that, I had a couple questions from earlier, too, that I thought would be important. I think I'll start off, though, to focus, again, more on your models. If there's one thing you could change right now to improve the model, what would that be?
Well, I think I'd like to change a lot of things in a model because I know we have a lot of problems. I think the one thing that is the single biggest and holds us back from being more quantitative is clouds. Clouds. Just the water cycle in the atmosphere is uncertain. We have trouble in measurements because satellites are not able to pull down some areas of the atmosphere very well. Until that gets more quantitative, we can't really underpin our theoretical knowledge. So that's one area where I would really invest in terms of improving the models.
Great. And earlier you mentioned the smog levels and how your models are predicting sort of the effects that then affect the increase in smog. I'm wondering if using those models and demonstrating that potential increase in smog, is that a case then we can make for the impact on public health, and that for perhaps those people who maybe aren't able to connect to the issues of climate change, but maybe can connect more to the potential negative consequences on public health. Do you see that as an important way to kind of link your models to those issues?
Yeah, absolutely. I think that's definitely one way. I think we have to study more cases of these in order to be convincing that, on even a statistical basis, you are able to explain a lot of these events, particularly during heat wave times. And also there is, I think one thing that the medical community is increasingly asking for is more quantitative details from us, so that then they can make their own determination. Because right now, even during the Chicago, remember the Chicago heat wave and a lot of mortality then, they're not necessarily able to explain as everything being due to necessarily heat wave, because there's a multiple stress thing involved where, a person who may have been disabled or is elderly had, let's say, preconditioning medical problems, which cause them to kind of react to a very low threshold. It is that kind of information that the medical community wants to get to, but they cannot deal with the uncertainties that are coming from the atmosphere and climate side.
So I'm thinking about our high school students here and many of people in the audience who maybe this is the first time they've ever seen kind of this quantitative information about the models presented here. When they leave here and they need to explain to their family members and friends what these models are showing, what's a good layperson's explanation for what these models are really showing us?
So climate is non-stationary, I'll repeat that again, but the quantitative aspects, that's kind of what you get from the models. I think increasingly the models are getting complicated, but you can actually do experiments with the models and make them toy models to answer questions. It's always going to be important to construct the questions for which you need the model, because otherwise it becomes an exercise in just building more and more complicated castles. But you want to ask the right question. And to ask the right question, you may be able to construct a model that is far simpler and is able to answer the question that you want.
So with all this evidence, all this quantitative evidence that you're demonstrating, you're doing these predictions, and you're showing that your predictions are matching what actually is happening, why are there still deniers out there?
Oh, they had to ask them. I don't know. I think, as Mike said in response to one of the questions, scientists are big skeptics themselves. I mean, most scientists are conservative. I mean, they will not believe the first time they get some result. They'll kind of want to do it again. And then after that, you want to make that knowledge available to everyone. You submit a paper for review. And you get totally hounded by reviewers because, especially if it's something new, people find, lots of problems with what you've done. Then when you cross that, then you get into assessments. And assessments become a higher pinnacle of objective judgment. And, sometimes people will get papers in Science and Nature, and then they will not get reported in the assessment because somebody found some technical flaw. So it is a big mountain to conquer, just kind of by way of proceeding along the scientific axis. Whereas I think the same question should be asked of deniers. What is your pathway to proving something? It's not enough, I think, to submit commentaries and opinions in newspapers. That's not objective. So I feel that there is a way to do this, and it's still not probably perfect. But you got to keep chasing it till deniers may have a point. I mean, maybe CO2 doesn't absorb radiation. All the things that we knew from 100 years ago is wrong. But somebody has to prove it, and prove it in a convincing document, in a convincing paper.
So along those lines, someone from our audience is asking, do any alternative physical models exist that can explain maybe some of these climate effects without including the human sort of intervention?
Not that I know of. I just don't think they exist. It's very difficult. I mean, as I said, it's not. You can forget about just surface temperature, but all these other things are also changing. Why are they changing? Can one explain simultaneously everything? That's kind of the key thing. And I think, I think all the scientists acknowledge that there are still uncertainties in even the explanations that are being given so far. But uncertainties can go either way. they need not just reduce the degree of explanation that you've given for human influence. They can actually make it more convincing too. It goes both ways.
So along those, I mean, it's great that we have the community, that we have the climate change community studying these aspects of climate change and doing these models. Maybe could you talk a little bit more about how the models across the community are different, and maybe how of course, there's different uncertainties and different models, and how those differences, how great are those differences? A little bit more, you talked a little bit about uncertainty and error, maybe a little more on others in the community and what they're finding.
So, as Michael pointed out, there were 30 odd models that appeared in AR5 in 2013 IPCC. There's probably going to be more in the IPCC that's going to start and culminate in 2022. I think there's some fundamental things that are common across all models. You'll find all the models reproducing some things very well, and some things they will differ. And that's kind of where the test is, because you have to understand the reasons for the differences between the models on some parameter that is not being simulated the same way in all the models. I think the Arctic sea ice reduction was one of them in, I think, the IPCC previous to last one, where a couple of models did get the reduction, but some others did not. And then I think the sort of question that arises is, are the models getting the right answer for the wrong reason? Are they getting it for the right reason? So there is actually an international intercomparison exercise that takes place about once in 5 years, which actually examines all these model results and makes these results available in the public domain for anyone to examine them and query them. And a lot of people get lots of papers trying to examine these models, finding that some are different from others. So there are mechanisms in place to intercompare the models, to make them, to highlight for people kind of flaws in the model, strengths in the model, weaknesses in the model, which then is a motivation for the models to go and improve upon themselves in the next round.
Sure, absolutely. So what are some of if we kind of think about the political climate we're in, I've heard some politicians sort of point out some of those weaknesses. Can you talk a little bit about what some people are saying about those weaknesses and why they may or may not be right?
I think one of the weaknesses people point out to is the measurements. Not just the model, it's the measurements. But I think a lot of them are pursued in good faith, and I think have been largely put to rest, especially sea level rise is one of them, for example. In terms of modeling, people will comment on, one of the comments has been that models have not taken into account certain things, certain factors, like maybe they didn't factor in the sun's changing output. Well, then people go and study that to see how much has the sun's output changed, because of course that could also explain the greenhouse warming, but it isn't much. It just isn't much. You can't just get something out of it. So it's very easy to sort of lob questions, and rightfully so. But in every case, there's nothing has come up which has negated the conclusions coming out of the consensus of the models. So there are things that people say, this model doesn't have it, this model doesn't have that. And the models are different in certain parameters, like, for example, clouds, which they represent differently, which is why there are actually, in principle, there are different models, because everyone is chasing their own theory. Right. And we are not able to constrain that. So that, I think, would be the one thing that we would admit, that we haven't constrained that well enough, but it doesn't, take away the fundamental conclusion, though.
Sure. So we have a good question here. Have the seasons shifted because of climate change?
There is actually a paper or two which actually suggests that the growing season has expanded. I think it's mainly right now it's in the observational territory to say whether there is kind of it is statistically significant or not. I don't think the models are in a position to address that question simply because the noise would swamp any signal that's coming out of the models. Although models which have run out to 2100, they somehow see that. But again, I think I would not put much credence in that because it's maybe only in a few models.
Interesting. I guess we'll have to keep taking data to definitely see what that impact might be. Sort of a general question maybe next around climate change, and this is, outside the category of models per se, but really why is the impact of carbon on our planet, why is it so large? Why haven't we sort of evolved to manage that increasing carbon amounts in the atmosphere?
So I think there are two questions there. One is what, the second part of it is the managed part. I think the management part really didn't quite arise till maybe 20, 25 years ago during the Rio Convention. People had been thinking about it, but it never really formally rose to the world stage. On the first part of your question, I think that there has been knowledge, certainly, on the subject. And why it absorbs, why it is such a potent gas, there's sort of a technical aspect, which is it absorbs in a region of the electromagnetic spectrum, which is nothing else absorbing. So, and there's a lot of energy available in that part of the spectrum, so that's where it absorbs. But I think on a more more longer time level, if you look at paleo data, there's been a lot of times when CO2 is varied by quite a bit. But it is not, that variation is not, unless you go way back in the Cretaceous, when the dinosaurs existed, there is not that much variation as we are seeing in the last, million years in the CO2. So it has been a gas which just increased. But one other thing is that it's not just the CO2 that's a problem. We have water vapor in the atmosphere, water substance in the atmosphere, and we have lots of the Earth covered by oceans. So when there is any warming going on, or actually any cooling going on because of some agent, the water reacts. And it is that feedback that actually is a major cause of the warming. If you were to ignore more sort of complicated feedbacks due to carbon and so on, about 70% of the warming is coming because of the increased moisture in the atmosphere, because water vapor is such a potent greenhouse gas. It's even more potent than CO2. And so the CO2 increase, or even methane increase, triggers the water vapor changes, and that's kind of why you get this massive warming. So it is CO2 induced, but there's a feedback from water.
So I guess then the follow-up question, since we are at Case Western Reserve University and the Great Lakes Energy Institute here is catalyzing research to mitigate some of these issues, are there innovations around trying to deal with some of these effects that you see kind of on the cutting edge, on the horizon, maybe that people are working on right now to help solve some of these problems?
So I think I would say that this information from the science is important, and therefore the science has to continually work towards making things less uncertain, more quantitative to the extent it can. But I think in terms of the technological solutions, there are, I think Mike had a plot which showed geoengineering, which showed carbon sequestration, etc. I think those are solutions in terms of the mitigation direction. But the adaptation direction might actually also be equally important, such as I think Stephen mentioned the coral reefs providing the breakers for the waves. Heck, that's sort of a natural thing. Why not try to take advantage of that? Yeah. Or the dikes that the Dutch have around their country, protects them from their land, which is below sea level. So sometimes the innovation may be entirely in the adaptive direction.
You know what I think would be interesting is as we have all these sort of great creative minds, if there's a way to take your models and take a potential innovative solution and integrate it into your model to see, hey, what is the impact then of changing sort of, the waves and how they break on the shore, or even how to capturing CO2 in one way or another is going to actually impact. Are we talking about, can we actually achieve a couple degree change, or is it really such a minuscule change that while the solution may be brilliant, the impact will be small? Is there a way to kind of bridge those gaps?
Absolutely, absolutely. I think, and especially that's kind of one of the reasons why we, not only we, but other modeling centers too, are going towards the high resolutions, because problems are becoming local. The global problem is, I won't say solved, but there's a very good knowledge about it now. But what's happening in the local scale, regional scales, that's kind of where we have to get to. And that's where these innovative measures being planned on the local scales, you can actually then test it in a model to see how much of a bang you're going to get out of it, and therefore invest appropriately, resources into that. So it can be done. In fact, I think in Germany, they're actually doing that in terms of examining what carbon sequestration can potentially do to reduce the atmospheric concentration. And I'm trying to think, Australians are trying to do something to repair the barrier reef, the golden barrier reef, which has been extensively damaged, and they are trying to now put ideas into the models to see how much can they reduce it by doing something in the corals, and how much of an investment it is. See, because I think the cost-benefit ratio enters into this.
Sure.
So tying an economic model
Sure.
to this is an absolute must, and I think it can be done.
Yeah, no, that's great. So one final question. This came from an audience member that I was chatting with at the break. And the question is, if these climate change models are relatively accurate, then why can't we predict the weather 3 days from now?
Oh, you can?
No,
That's a flippant answer. No, I think you can. I think that's a test, though. There are certain modes of climate where the weather can be predictable, This is a general answer. I mean, I'm not saying that we can actually do this, but there are some states of the ocean in the Atlantic and the Pacific that actually make the weather much more predictable over the U.S. land areas than otherwise. So it is not as if there's going to be a general solution. Like, if I know this, I can predict the weather 2 or 3 days in advance. However, if the Atlantic is in a mode of variation that is of a certain kind, perhaps we can. So this is research. I mean, this is kind of where research has to be done to explore these possibilities. But they do exist. They do exist. 3 days is actually not a big problem. I think it's the seasonal now that is the main issue as to whether you can do a season in advance. Because, I mean, if you knew on June 1 what the Atlantic hurricane season is going to look like, a lot of people will benefit, a lot of sectors would benefit.
Good. Okay, well, thank you again, Dr. Ramaswamy.
Thank you.